Welcome to Algorithms with Professor Caleb. Today I want to talk to you about Heapsort. So the basic concept behind Heapsort is that we're going to build a max heap, assuming that we're sorting in ascending or non-decreasing order. Then we're going to repeatedly delete max, swapping the root value to the end of the heap. When we have one item left in the heap, we will have our sorted data. So the first step will be to build the heap. So we're just going to make sure that our data is in indices 1 to the number of items, because of course we need for our root to be at 1. Then we're going to use the linear time algorithm, that heapify algorithm I've talked about in one of my data structures videos, to turn the array into a heap. Suppose we have this data, everything is in 8 through 13, that's the 7 items we want to actually sort. The 7 is just there to indicate, okay, I've got 7 items in this heap. So our last parent in this heap is at index 3. 7 divided by 2, 7 items. And so we're going to swap the 13 and the 3 because we're building a max heap. So I'm going to pull the largest item, largest child of that 3 up in place of it. At that point, we're done with this percolate down because the 3 doesn't have any more children. So now we go to our next step, which will be to do a percolate down from the 2. So we look at its children, which are 16 and 11. The 16 is the larger item. It's bigger than the 10, so we do that swap. And that percolate down is finished because there are no children from 4, so 10 doesn't have anything else to compare to. Then we're at the root with the value 8. We compare to its 2 children, which are at the 16 and 13. We swap with the 16, but we do still have children to check. So the 8 is going to compare to the 10 and to the 11. And we're going to swap with the 11. And now we're done because the 8 has no children. So at this point, we have our heap. And now we're ready to actually sort. So now the steps that we're going to take are to do this delete max thing until we've got only one item left, making sure that we put it at the end of the heap each time. We start out with the whole heap, which is the heap we had at the end of our heapify process. We're now going to do that initial delete max, swapping the 2. So the 16 is now in that last item that used to be part of the heap, and the 3 is currently the root. Now, of course, our heap is broken, so we're going to start working on percolate downs, ignoring, of course, that last item in the array, which is already sorted. So we compare the 3 to the 11 and the 13. It needs to be swapped with the 13. Then we need to continue the percolate down and compare to the 3's 1 remaining child, because of course the 7 is no longer part of the heap. And we swap the 6 and the 3. Now we need to do that next delete max. So that swaps the 3 and the 13. So the 13 is no longer in the heap. And then we need to start fixing things. So we compare the 3 to its 2 children. We need to swap with the 11. And the 3 still has children, so we need to continue that percolate down process and swap with the 10. Then at the next step, we're ready to do the next delete, which swapped the 11 and the 8. Now we start the percolate down process. So we swap the 8 and the 10. We check the 8 against the 3, but there's no swap needed because the 3 is smaller than the 8. So we have the heap. We're now going to do the delete max. Again, swapping the 3 and the 10 this time. We now start the process of fixing our heap. The 3 is compared to the 8 and the 6. The 8 is the larger, so we swap the 8 and the 3. The 3 has no children, so we're done with that percolate down process and ready to do the next swap, which will be the 8 and the 6. So now we do the percolate down, but we don't need a swap because 6 is bigger than 3. So now we're ready to do that final delete max, which swaps the 3 and the 6. At this point, we have only one item left in the heap, and so we are done. We can see that if we look at the values in indices 1 through 7, we have our initial values in sorted order. Of course, we're ignoring index 0 because this is using a heap. We're working from index 1. What's the performance of this like? Step 1 is that linear time heapify or buildHeap algorithm. So that's big O of n. Then in step 2, we had n-1 delete max operations because we deleted each thing from the heap except for the last item. A delete max operation is big O of log n. So that means we're doing n-1 log n operations. So that leaves us with the conclusion that step 2 is big O of n log n. So then to get our total performance, we need to add big O of n plus big O of n log n, which in big O terms, we always are only keeping the largest term. So that's going to be big O of n log n. So Heapsort's advantages are that it's guaranteed big O of n log n performance. Best case, worst case, all cases, we've got n log n performance guaranteed with Heapsort every time. We also like the space cost of Heapsort. So we have n+1, technically n+2, because we do need one more space in that array to hold our data because we're keeping track of the size. Then we have the item that we use for the swaps. This is competitive. We don't do much better than that. On the other hand, disadvantages of Heapsort. It does have a higher overhead in terms of constant factors on the time than some of our other n log n sorts. So we'll find that while it's n log n and beats the n squared sorts, we do find that as we compare it to some of the other n log n sorts, it may be a bit slower. It's also not a stable sort. So one of the things we care about with sorting at times is, do we keep values with the same key in the same order? This does not, because we're doing the heaps for the same reason that with priority queues, it doesn't keep all of the items with the same priority in order. Same is true here. This is not going to preserve anything about your original order. I hope you found this helpful and that you have a better understanding of Heapsort than before you started watching the video. Thanks for watching. Hope to see you next time.